All right. So continuing with the discussion of the D2As and data converters, the D2As are devices basically that convert the digital data to analog data, and they have certain metrics. We talked about those about like the nonlinearity and gain offsets and things of that sort. So there are many different ways. There are several different ways to implement a D2A, and we'll talk about them very briefly today, just like very briefly. So this is a super high level introductory level discussion of D2As. Now, the first way of making a D2A, so we're talking to digital to analog converters, sometimes called DACs, etc., or D2A. So there are different ways to generate different digital levels. The idea here is to be able to generate different digital levels and be able to select them. The simplest of them is, the most straightforward, is basically when you have a V reference and you have a resistive ladder. So you have a resistive divider ladder, and then you have something like this. So you come down. These resistors are nominally the same, meaning that basically you want them all to be of the same value. So here, and you have n resistors. So if you have n resistors, basically this point, this voltage is 0. This voltage is Vref. So it's a resistive divider. So all of them are Vref times something, times 1 over n times R. 1 over n, because you have R and you have nR overall here. So here is going to be Vref times 2 over n, and so on and so forth. So this is basically Vref times n over n. And the one before that is going to be Vref times 2 to the power of, I'm sorry, actually this should be, if there are n bits, let's call this 2 to the n, if this is capital N. So there are 2 to the n resistors. So this is going to be 2 to the n minus 1 over 2 to the n. And this node would be Vref 2 to the n minus 2 over 2 to the n, and so on and so forth. So you have these voltages established, right? These are all the voltages you would need for an n-bit DAC. So you have created all these things. And we saw that, we talked about this briefly, and you can see that this is ideal, of course. There would be mismatch, and if there's mismatch or if there's gradient in them, that would correspond to INL, DNL, or INL in the response of the DAC. But now, one of the things that you would like to do is that basically just take these voltages and select the right one. So that's the simplest thing that you can do as a D2A. And one of the things that you can we discussed briefly is a network of switches, right? So for example, you can apply your first bit, let's say, so this is B0, the LSB, and then B0, so B0 bar, B0, and then you select a pair, right? This way you have B0 bar, or let's call it D0. D0, digital 0. So this is D0 bar, D0, and so on and so forth. So this network basically allows you to select between whatever value that you need, between one of the two, based on the LSB. So this is D0 and D. So the LSB. Now, this one, the output of these branches, is essentially selecting the right segment based on the LSB. And of course, you can continue doing this. This is a very simplistic thing, right? So now you take this one and the one that comes underneath it, and then you apply D1. And the same thing here. So you apply D1 bar and D1, and you continue doing this, pairing it down through multiple branches, until eventually you get to your V out. So what this does is that through n switches, you will get connected to one of these branches, because you will have any branch would take n switches. So this may sound simple and relatively straightforward, but it has several problems. Obviously, it has no driving capability. You're looking at some sort of a passive network. You will have a time constant that would depend on how you connect, where you connect. Because if you connect the middle of this branch, if your voltage is around here, you have two large resistors on both sides. If you're at one of the ends, you have a smaller resistance, so you have a different time constant associated with the inevitable load capacitance that would be here. Also, you don't have drive capability, so it would be slow. There are other questions about this, of course, the quality of the matching and all those things, but this is some sort of a D2A, right? If you will, this is some sort of a poor man D2A. You need some sort of buffering, you need some amplification, and then that could introduce additional errors if you put that there. But anyway, it does work if you make something like this. Now, what else can we do? So this is one method of deciding the output, right? So this is a resistive divider. And there are variations on this to make it a little bit more clever. You can do interpolation, things of that sort, or the switch arrangements can be a little bit more clever, the way you do things. But that's the essence of it. So what else? What else can we do? What are the other categories of things that we can switch? So one of the other things we could do, in principle, is to have multiple currents. Because if you have a current, you have the drive capability. So how about we switch the currents in a digital fashion? So what is the simplest way of doing that? So imagine that you have a bunch of current sources. Excuse me. So let's say you have a current source. One direction or another doesn't matter. So let's say you have a whole bunch of identical current sources. Let's start with that. So you have a bunch of identical current sources. And then you have switches attached to them. And then let's say you aggregate them and then put them into some sort of a resistor. Now, let's say all of these currents are like whatever, I0, I0. So is there a certain kind of code that we can apply to those switches for this to act as a D2A? Thermometer code, right? I mean, we can basically just turn the sufficient number of switches on, right? So, but if you need an 8-bit D2A, what you need to make is 256 current, or 255 really, current sources, right? 2 to the n minus 1, and then you turn as many accordingly as, so you basically what you need to have some sort of a binary to thermometer converter, which is a combinatorial logic. It's a simple combinatorial logic circuit. And then your digital input comes in, you generate thermometer code, so you basically get T0, T1, T2, all the way to T2 to the power of n minus 1. And you just turn them on, you just drive current into a resistor. And now if you have a capacitor there, that's fine, because now your time constant is primarily determined, assuming these are ideal current sources, is determined by that RC. So you just drive the current into that, and then whatever time constant there is, but you have drive capability because you have current sources. These are active, right? You can drive it. So this is a very simple, really simplistic and simple A to D, D2A, right? Now, this is fine. What is the problem with this? Can you see a problem? Something. What are the problems and advantages of this thing? Let's say, is there an advantage to this? Well, it has drive. That's fine because it's current. It has relatively constant time constant, which is good. It also has another quality. I would claim that the DNL of this thing can never exceed 1 LSB, and it's often much less than an LSB. In other words, it's always monotonic, right? The output is going to be, with respect to the digital input, is going to be monotonic. Because you're always kind of throwing more current or less current, taking more current. As you increase the number of current sources, you just either add more current or less current. Now, your steps may not be exactly equal. So your output steps may not be exactly as you want them ideally. Ideally, you want this to be like this, right? The steps to be ideal. So yeah, some of the steps may be a little bit larger. Some of the steps may be a little bit smaller. But it would still be monotonic. You don't run into a situation where you go from one bit arrangement to another bit arrangement, and all of a sudden, just like the output, instead of going up, it goes down. Assuming that the second bit arrangement is higher than the first one, obviously. So that's a good thing about it. What's the bad thing about it? What's the problem with this? Yes? Variation among the current sources always, yes, exists. That's correct. That's a problem anywhere. It does exist. Correct. What else? Take it? Heat. Yes. That is correct too. You generate heat because you basically have a set of active things. But if you have a driver, if you have something that drives, usually you generate heat, right? I mean, the trade-off is that you do, if you want to move something, you need to spend power. I mean, you need to spend energy, which basically means that you need to have power, and then you have power consumption. That is correct. There's this obvious one, right? If I wanted to make, let's say, a 16-bit or 14-bit or 12-bit D2A, how many of these current sources would I need? Let's say 12-bit. I need 4,000 of these, right? 4,096 to be exact. 2 to the power of 12. So you can, and more importantly, you need to wire 4,000 digital wires to these kind of like switches in an efficient fashion. That comes out of your combinatorial logic, right? So your combinatorial logic has 12 bits input. So this is, in that example, this is n, but this is 2 to the n, right? So it would be 12 and 4,096, right? So it can grow out of control pretty rapidly, especially the digital wiring of it. So can we come up with a way of making it more compact? Yes?
Have the current sources be powers of 2?
Current sources be powers of 2. Okay, that's right. Any other, was that a suggestion? Yes. Okay. So, or correct. Another way of saying is that just basically group them in powers of 2. So you can have 1 and 2 of them grouped. So basically make a current source that's twice as large. So what would that look like? So for example, here you have I0, right, with a switch. The next one, next current source can be 2I0 with a switch. The next one would be 4I0 with a switch, and so on and so forth. And the last one would be now 2 to the n minus 1 I0 with a switch. I mean, this is kind of conceptual still. But that's the concept. Now, the good thing is that you can actually apply, instead of T0, you can apply D0, the digital data. Well, if it's D1, sorry, you have to start from D1. D1, D2, D3, Dn. I should have started from 1 there too, doesn't matter. But OK, so we can do this and then drive a resistor. So now we've reduced it. If we had, for example, a 12-bit DAC or 10-bit DAC, we've reduced it to 10 devices as opposed to 1,000 or 4,000 in the case of a 12-bit. So that sounds like a good thing, right? It's much more compact. But do you see any disadvantage to this? Is there a can you mention a think about a disadvantage? Yes?
Well, in one manufacturing process, now you have to be able to make 2 current sources that are 1,000 times different.
Right. You have to make these, for example, 1,000 times. This current source is 1,000 times larger than that. Not only that, but also it has to be accurate to the precision of that smallest one. Now, one thing that's very common in these kind of things, in this kind of D2A, one of the things that you will see is that you may see something like this at some point. In the response. Why would that happen? It can become non-monotonic. Yes?
Because a larger current source is kicking in, and the error in that one outweighs the
right. Exactly. So for example, imagine a scenario where, let's say, I don't know if it's let's say it's a smaller number of bits. So let's go through whatever, let's say 8 bits. Okay? So you go from this bit sequence to this bit sequence. Right? When you transition from that. Right? So for example, you're going from 8F to 90, right? In hex. So if you're going from 8F to 90, what's happening? You're in this configuration, right? You have all of these current sources on except for the last one. Now, when you go one bit higher, you're turning all of them off and you're turning this one on. Now, for this to stay monotonic, they have to be accurate to the LSB. The sum of all of those things has to be accurate to the LSB. Now, if there's a small deviation in these, this change can be large. It can be in one direction or it can go in the other direction. It can actually be a big jump here in that direction, right? And what is most pronounced in these things, actually you will see it. So let's say if you go to the full range, to the 2 to the n minus 1, so what you see is that you will see the largest jumps here in the middle, and then you see 2 smaller jumps here, and then you see 4 smaller ones here, and things of that sort. Because that's when you're transitioning from the largest current source to the next one, or the second largest to all of them, and so on and so forth. So that kind of thing can happen, and that would be an issue. But in principle, you can make this. Now, usually you make these things up to 8 bits or maybe 10 bits or something like that. When you want to go to higher levels, then the levels of matching required makes this not very good and reduces the resolution, practical resolution or effective number of bits that you get out of these things. So how do we make these current branches? How do we make these, let's say, scaled current branches or even non-scaled current branches? Excuse me. How do we do that? So let's talk about some of the implementation. I mean, we've talked about this in a different context before, more or less. But let's talk about them again in this context. So let's say the simplest things you could do is that you can have a current source and you can divide it, right, among multiple devices. So let's say you have one current source, and then you can make identical devices here. And so on and so forth, and then use them as your sources of current. Now, so let's say you have one I total. So let's say this is if you wanted to do a thermometer code example. You have a bunch of current sources like this. Can we use it, by the way we described it? So can we just have a switch now here, and then connect them to whatever? No, why not? What happens if I just do that? You
always need to get I total first.
Right. So it means that when the ones that you turned off, their current will end up in the other ones, right? So your currents will be unstable. So how can you fix that if you wanted to do this? This is not really the great way of doing it. But what you needed to do, you have to have another branch for each one of them going to VDD. So the current is either going there or going to VDD. You have to dump the current. You have to take care of it. You can't just like leave it open. You either throw it directly through VDD, or you send it here and pass it through some sort of a resistor to VDD. That's one way to do it. And if you want to have a scaled one, how would you do that in that case? And then a scaled version of that would essentially be similar to that. Let's just say, okay, I'm going to do a bunch of these. I'm going to do batch processing. Okay, and then you have, so you can actually, if you wanted 3 bits, for example, IREF, you could do that. You can clump these, and then you have essentially these are at some reference level, right? The same thing here. These are all VREF, some V bias. Let's not call it VREF, V bias. And then these are clumped together. So this basically gives you I0. This gives you 2I0. 4I0, assuming that you always are dumping the current somewhere, right? So you're either connected to VDD, or you're connected to the other branch where the currents are aggregated. And then you go to the resistor, to the VDD. Something like that. You can make something like this. Again, not great because you're really sharing the same current source that way, and then all sorts of kind of like interaction between them can be affecting you. So what is another way of doing this? Can you think of another way where you can actually decouple the current sources from each other? We can make reference branches, right? I mean, you know how to make reference branches, and we know how to replicate them. For example, in BJTs, you know how to do this. Let's say you can have a bipolar transistor, and then you can control the ISs, right? So you can have a transistor that has let's say this is IS, has a saturation current IS. Let's say this is IS. This is 2IS, 4IS, and so on and so forth. So you could actually do something like that. And then you have a reference branch or reference current that produces these currents. So is this OK? Excuse me. It's better than the other one, but is there a problem with this? Yes?
You're going to run into a transistor 1,000 times larger.
Yeah, you get into a transistor that's 1,000 times larger, so you have to think about when you make that, you have to make that really as 1,000 individual transistors, which is fine. Yeah, that's fine. Yeah, if you want to make an 8-bit one, then you have a transistor that's 256 times larger. So those are problems. That's a problem. We need to deal with that. But other than that, remember, for example, if they were made out of bipolars, there are a couple of problems here, right? Yes, because you basically what happens is that you have a lot of this base current being drawn here out of this, and it has to come from here, so it will affect it. So you may need to actually have something like this to buffer the current and get some gain on the base current, so you get a factor of beta advantage there. Now, what else? Is this good? Do you think this is going to work? Or are you going to run into the motor driver problem that I described to you a long time ago? You remember thermal runaway? You remember the VB had a negative thermal coefficient, so one of them gets a little bit warmer, the VB becomes smaller, so it basically draws more current, gets hotter, more current, more hotter, and all those things. So that's going to be a problem. And the way to avoid that was to produce some resistors here, right? So for example, if you wanted to make this, you need to put resistors here. And these resistors need to be properly scaled too, right? Because if this resistor is R, and this resistor is R, what should be the value of this resistor for it to carry twice as much current but not draw twice as much voltage? R over 2, right? So this is R over 2, this is R over 4, and so on and so forth. So you can scale them, and you can get something decent that way if you really wanted to make that out of bipolar transistors that way. That's fine. Now, how about MOSFETs? If you wanted to make multiple branches with MOSFETs, you could do it this way, a similar fashion. You don't have the thermal runaway issue or the gate current issue in the case of a MOSFET, or at least the traditional MOSFET. And then you basically can do this, and then you make this W over L, 2W over L, I suppose, and 4W over L, right? And then these are your 3 branches of current. And then you can switch them on and off, right? These are some things that we've looked at before. Now, do you think this is a good way of implementing it, just making it W over L, 2W over L, 4W over L, the way we did it? Well, it depends on how you lay it out. When you do this kind of thing, the layout is important. So let's think about this. Let's imagine this is your reference transistor. Let's say it has a single finger. So this is the drain, this is the source, this is the gate, right? So this width is, this is W, and this is L. Now, if I go and implement this other transistor would look like that. That's fine. The next transistor, I need 2W over L. So one of the things you could do, you could actually have 2 of these things. You can say this is a source, this is a drain, this is a source, and this is a gate, and this is a gate. So you have 2W. So this is still W, and this is still L, and I get 2W over L. Or I could implement it like this. I could say, no, wait a second. I make it twice as long. So this is 2 W's, and this is the L. Or let me propose a third way. Make 2 like that, drain, source, gate, gate. And of course, I short these, I short these, I short these. And here, of course, I've connected these two. But, so we have 3 designs, 1, 2, and 3, right? Is there any preference to any of them? Which one do you prefer? 1, 2, or 3? How many people prefer design 1? Raise your hand. Okay, nobody. How many people prefer design 2? Okay, nobody. How many people prefer design 3? Some of you. Okay. The other people have no preferences. They don't like any of them, I guess. But, okay, so why do you prefer design 3?
You could interpolate the various fingers between your different current sources to try to counteract gradients.
You can basically, okay, so you can interleave them. You can so that's a good, nice secondary argument. That's good. We will get to that. But even primarily, which one of these things has a better chance of being carrying exactly twice as much current as the other one? Number 3, right? Because there are 3-dimensional effects in this thing that we're ignoring, right? If the field on the side, things of that sort. So either one of these things are not an exact double of that. Well, double. They're not exactly twice the size of that, right? Here you have 2 identical ones. It's a little bit bigger, but they are going to match that better. So you implement it really the way you're implementing is not this. The way you're implementing it looks really, truly like this. Or 4 of them here. And then you're shorting them. So this is an important thing, the way you arrange this. And then you raise a nice secondary point. You said, look, you have how many of these transistors? Let's say you have an n-bit D2A. How many transistors, how many of these unit transistors do we need? 2 to the n, right? Because you have 2 to the n minus 1 here, and then you have an extra one for the reference. You have 2 to the n. How would you arrange them? Well, you can arrange them, for example, in an array, right? You can make a square array. Something like that, right? These can be arranged in an array, and you place them, and then you connect the wires to the ones that you want. Where would you put the reference one, by the way, roughly? Center. It's probably a good place. So this one in the middle is going to be the one here, because it's kind of middle of everyone, right? It sees the same effect. Now, what else do you do? So then you can arrange them in different configurations, right? You can have like different configurations so that basically you minimize you can go in terms of like go around this in certain ways and connect them that way. You may not be able to do it perfectly, but you can try to make arrangements that are conducive to that. For example, the next 2 could be here and there, and the next 4 can be like, for example, here, there, et cetera, and so on and so forth. Or other arrangements, you may actually put them here in the corners, and then the next ones. And you can go basically based on that. You can arrange them in a symmetrical fashion. The other thing that people do often is that they actually put at least an extra row if you want to make them have good matching. If you're making a 6-bit D2A, none of this matters. If you're making a 12-bit D2A this way, then all of this matters, and then some. They put a bunch of extra ones around this entire active array, and they don't connect it to anything. We call them dummies. Why would you do that? Why would they do that? Yes, Richard.
Make sure the outside row experiences a similar fabrication process.
Correct, because in the fabrication process, if the arrangement of things that are next to it are a little bit different, they may get a little bit exposed differently, right? They may get more implantation, less implantation, coverage. Etching may be a little bit different because there's more etchant available on the edge because the adjacent ones are not being etched, so they can get over-etched. So you basically have an array. Sometimes there's 2 rows, 2 sets of these things around this to cover it. And this way you create an arrangement that is more conducive to this. And this is not limited to this, by the way. There are cases where we make capacitive devices, and we'll talk about those. The same thing with the capacitor. If you have arrays of capacitors, these kind of arrangements are common because it allows you to maintain certain level of matching and accuracy and precision. So that's all good and nice. Now, the other problem here that you run into potentially is that if you do it this way, if you think about these current sources are not ideal current sources, right? Even if you go to the thermometer coded one, if you go to that one, let's go back to that original one. Even in this case, these are not ideal current sources, right? They have an output resistance. There is no such thing as an ideal current source or an ideal voltage source for that matter. They have output resistances. Now, what you will see is that depending on which switches are on and which switches are off, the output voltage would be different. In fact, what is the output voltage? The output voltage is going to be the current, let's say N transistors are on, Ni0, times the total resistance you will see in that case. What is the total resistance you will see? It's R1 parallel NRO. Right? I'm sorry. RO over N, not NRO. RO over N, because they're in parallel. Right? And so that's the parallel combination. You can actually write an expression for it. Right? So this is V out. And then you can write it as Ni0. When you multiply it out, you basically get, I believe you get, so let's do it. So you get R1 RO0 over N divided by R1 plus RO0 over N multiplied by N, you get Ni0 R1, or you can absorb that like this. You get IO0 R1 N RO over RO plus N R1. And you can see this is not exactly monotonic with N, right? Because of that N in the denominator. So this does produce an INL. This does give you something that doesn't look straight line, like straight line. And you can calculate what that INL is. And I think it is basically the maximum amount of that INL is I R1 N total N squared over 4RO. So this is INL max. I mean, you can calculate. You can use that expression calculated. It's just basic algebra to do. So you can see that even that output resistance now becomes important, and it becomes something that you need to really worry about and be concerned with. So how do we deal with that? Can you think of a way of dealing with that? If this is the issue. I mean, that's an issue for all of them, really. Right? Because the output resistances are going to be different with different switching. So how do we deal with that? How can you minimize the effect of that output resistance?
Make it as large as possible.
Make it as large as possible, right? But that's determined by the device processes, right? So there's another way, right? There are two ways to be the best. Do better than other people or make other people do worse than you. That's not a good way. I mean, some people do that, but I don't think that's the best way of doing things. So make other people do worse, right? So if you can't make this as large as possible, then make this as small as possible, right? Make R1 as, it's the relative value that matters. So if you make R1 just small, what will happen? Well, you will get less of this effect, but also you will get smaller voltage. Because your eventual voltage is determined by the total current that you put in there and the resistance, right? R1 times I, or Ni. So what do? Well, you can use a transimpedance amplifier. You can actually use the feedback. You can use op amps, right? So if you, for example, use an op amp in a simple configuration with resistor, a negative feedback on a resistor, what happens to the input resistance? We've talked about these things extensively. Right? What happens to the input resistance? It's a shunt configuration at the input, so the resistance goes down. So you see a smaller resistance, but all of your current would go where? So this is going to be a small resistance. But all of your current that you inject, instead of injecting into this, so this current will go straight through here. And this voltage, if this were an ideal op amp, this would be virtually equal. So this would be close to 0. So this output voltage would be given by that current going through R1. Right? So you can use an op amp like that. Now, is that free? No. You burn power for the op amp, but also there's another price that you pay. Your speed is going to suffer, right? Because now you're limited by the bandwidth of whatever this op amp under that feedback configuration is. So you need to kind of make sure that the op amp under that much feedback is stable and doesn't ring and has the right bandwidth and things of that sort. So you now have to deal with all those issues that we've dealt with before when you have feedback in the system. But yeah, that's one way to get rid of that. So that's another way to think about this challenge. All right. Okay. Now, the problem we were running into in these arrangements is what? Is really the fact that we are trying to get very large ratios of currents or devices, right? We are trying to use devices that have very large ratios. And the larger the resolution of the D2A that you're trying to make, the larger this ratios would be. Or you have like large currents and small currents, and these kind of things can happen, right? So is there a way to avoid that? Is there a systematic way to use components that are more or less on the same scale? Well, there is. Now, and it's kind of almost, it's a really cute small thing that, in my opinion, is kind of somewhat magical, and it's very simple. And you probably have heard of. It's called the R2r ladder. R and 2r ladder. So what is an R2r ladder? So let's draw an R2r ladder. So imagine you have a ladder of resistors like this. So the first one is an exception, is R, but every one down here is, the horizontal ones are R, and the vertical ones in this arrangement is 2R. Now something really interesting happens with this ladder, and you keep going. And of course, you can see all the components are either value of R or 2R, so they're on the same order of magnitude. They're not going to be drastically different. Now let's imagine you have current sources driving, well, let's say they're driven into the thing for now. And so on and so forth. So, and this keeps going. So let's see. So let's call this current source I0. Let's call this I1, I2, I3, et cetera, et cetera. So there are generally multiple current sources with multiple values. So what is the Norton equivalent of this part of the circuit? Right? How do we determine the Norton equivalent? We want to determine the resistance. We null the independent sources, right? So from this terminal, what is the resistance you see if you null the independent sources?
R.
No, to ground. So R and R, right? So 2 R's. 2 R. And then what is the effective, the short circuit current? If I short circuit here to ground, how much of the I0 will end up there in that branch? Half of it, right? Because it gets divided between these two. So do you agree that this is equivalent to I0 over 2 in parallel with 2R? Right? Do we agree with that? So I can take this out and replace it with I0 into that node and 2R, right? So, well, I can do it here by erasing stuff, or we can do it somewhere else. And let's do it here. So I'm going to modify it. I'm going to take this part out. We're going to take this. Remember this shape, this form, right? We're going to take it out and replace it with this guy. So what do we have? So now I have 2R, and I have I0 over 2, right? So this aggregate here, obviously what you can do is that you can say these two are what? These two are basically one current source of I1 plus I0 over 2, right? And then these two obviously reduce to a resistor of R. Now, do you see the similarity? What happened? We got the same structure, right? It's self-similar. So you got exactly the same thing. So now I can do the same. We can do the same exact thing, same argument, and say, well, this entire thing now looks like what? So now you take these two, and they get scaled down by another factor of 2. So you get I0 over 4 plus I1 over 2. So that's the Norton equivalent of that in parallel with 2R. And now we can take this whole thing out and replace it with that. And now you can see the recursive process, right? So you keep doing it. So by the end of this chain, the equivalent circuit for the entire chain would look like a single current source in parallel with resistor 2R, whose value is I0 over 2 to the power of n plus I1 to the power of n minus 1, all the way to I n minus 1. And then you have I n minus 2 divided by 2. So I n minus 2 divided by 2 plus I n minus 1. So you can see that this R2r ladder essentially scales the current sources for you. So you can have current sources that are similar in magnitude, and you can turn them on and off. If you really wanted to do that, you can basically just put switches here or actively turn them on through a control voltage. That's probably better. And apply your D0 here, or whatever, D0, D1, D2, D3. So your digital bits are applied to these current sources. So whether or not you turn them on and off, they would be either have the base value, so you can make them all equal, and then turn them on or off. So the overall response would be D0 times I0. If you make all of the currents the same, so you will have basically, you can factor I0 out. It will be I0 times D0 over 2 to the power of n plus D1 2 to the power of n minus 1, all the way to dn 2 to the, divided by 2, I believe, yeah. This should be 2, this should be 1, if you do it the way I drew. Sure. So that would be the total current, I out. And you are not using any two values, no two current source or two resistors that are drastically different. They're all on the same scale. It's a very commonly used thing. If you want to make resistive networks, that's probably the most common way of implementing it. So that's another way of doing it, right? So these were kind of like current source based and resistive based. Are these the only ways of doing D2A? No, there are other ways. How about using capacitors instead of resistors and getting your divisions based on capacitors? Because capacitors do charge sharing, right? When you do charge sharing, what happens is that you can actually take a certain amount of charge and share it differently between different components. So here's one example, just to give you a sense, to give you a feel for how these kind of things work. So imagine you have a network of capacitors. And on one side, let's say they're all connected to each other. This is your V out, essentially going to be V out. And then on the other side, you have a choice of connecting them either to ground. So you have ground voltages here. Or you can connect them to the reference, some Vref. So this is Vref, 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 Vref. So these switches can switch either to one side or the other. So this switch needs to be somewhere. So these capacitors, let's say they're all the same size. They're all C's. So C, same value. So if you have a network like this, now think about what happens, and then you need to have a switch here to ground too. So in the first phase, assume that all the switches are connected to ground. So in the first phase, you connect all of these switches to ground, and this switch is connected to ground. So all the capacitors are shorted to ground on both ends. All of them are completely discharged, right? Now imagine that you turn n lowercase n of the total n. So let's say there are total of, there's a total of n capacitors. Let's say you have turned n out of n, capital N, of them, connected n out of the n of them to the reference, and connected the other ones to ground. Actually, you connected n out of the n to reference. Yes, correct. So let's say n of them, we are using thermometer code here, right? Right? So we are using thermometer code. So we are connected n of them to the reference. So what is going to be the equivalent circuit? You have two capacitors, right? The other half are connected to ground, the other group. So you have n capacitors, so you have NC that's connected to Vref, right? You can think about it as a voltage source. And then this is V out. And the other n minus n connected to ground. So now what do you have? It's a voltage divider, right? It's a capacitive voltage divider in that arrangement. What is the voltage across this capacitor? Well, remember, the impedance, the voltage across this capacitor basically is just this impedance divided by the sum of the two impedances, right? But the capacitors basically are the impedance of a capacitor is 1 over Cs, so it's inverse. So when you write that, you easily see that V out is going to be NC divided by NC plus N minus NC times Vref, which gives you basically N over N Vref. So this capacitive divider network as a thermometer code can produce a digital output. I'm sorry, an analog output based on a digital input. So it's a D2A. Now, of course, this network doesn't have to be thermometer equally weighted. You can make it binary weighted, right? If you make it binary weighted, what you would do, you make this C, you make this 2C, you make this 4C, you make, I don't know, 2 to the n minus 2, 2 to the, well, n minus 3, 2 to the n minus 2, and 2 to the n minus 1 times C. And then instead of applying thermometer codes here, you basically apply the digital code, right? D0, D1, whatever. Dn minus 2, dn, well, dn minus 3, dn minus 2, dn minus 1. So you can make it binary weighted, and you can do the same thing. Now, if you make it binary weighted, you are dealing with the same situation, the same challenge with matching that you were dealing here, right? So you may end up having to make all of them as individual capacitors. You actually most of the times do. So these are individual capacitors that look the same, and then you just connect a sufficient number of them, the right number of them in parallel to produce those things. So it doesn't make your total capacitance smaller, but it makes your digital wiring simpler if you did something like that, right? So that's another example of D2A. Now, last discussion, I mean, very briefly about D2A. Can we do anything else? So we saw that we can actually basically have voltage division, we can have current division, we can also have charge division, right? So these are the basic three principles behind these three basic types that we talked about, really, right? So we have these three types. And is there anything else we can do? I mean, there are lots of other things we can do, but let's talk about one more thing. How else can we make it convert a digital input to an analog output? Yes? PWM. Very good. That's one way, right? So you can basically have a single bit, right? You can have a single bit that turns on and off. And you have a bit that can, so it's a digital output, right? So you can have something that turns on and off constantly. And so let's call this a PWM for pulse width modulation. And it's a single bit output, right? So what happens here is that the output of this thing can be either 0 or 1. And let's say you have equal intervals. For doing that, you don't have to, but let's say you have equal interval. And within each interval, you can start from different ratios of the time that you're on as 1 versus the time that you are on as 0. And you can go all the way on to being 100% 1 pulse width to 100% being off. That's called duty cycle. So duty cycle is the ratio of this length to this length, right? So duty cycle can be anywhere between 0 to 100% or 0 to 1. So if that's your duty cycle, now imagine that you put this, what's coming out of this thing, into a low-pass filter. What would you get? Well, if you make this low-pass filter sufficiently tight, you will not see any of this pulsation. What you will see is this the average voltage that's coming out, right? So by controlling the relative height of this thing, I may have been able to produce, for example, half a sine, right? Well, in this case, the DC, it would not go all the way to DC, just it would be something like that. And if I continue doing that, I could basically produce the rest of the sine wave, or any waveform I want. In fact, what matters is really the average of what comes out of here. So this is, like, let's say, the average of that voltage is going to be what? It's 1 over t, so let's say this is the period, integral from 0 to dt of V max, could be 1, dt, plus 1 over t integral from dt to t of V min dt. And if you write these two, you will see that this obviously just basically just these t's cancel. You get dV max plus 1 minus dV min. And if your V min and V max are 1 and 0, you can actually produce something where your average, your slowly varying average, so now I'm making that a function of time, can be basically determined by simply, so let's say V max is 1 and V min is 0. So it becomes basically that. So at any point in time, you set your duty cycle according to the height of the signal that you're trying to achieve at that point. Of course, this has to happen much faster than the actual data that the signal you're trying to generate, for you not to see the ripples. But this is a pretty simple thing. And then you can actually apply feedback around it and compare what you're getting with what you're receiving. So then that becomes, for example, a delta modulator. Or you can actually make it sigma delta modulator, delta sigma modulator. And then those basically can be used to apply feedback to actually not only achieve this, but also shape the quantization noise out, which we'll talk about shortly. OK, any questions on this?